now I hand over the today's first morning talk to be delivered by Professor M.A. Khamsi. Professor N.C. Wong will chair this session. So I request Professor N.C. Wong to come forward and chair the first talk.
Okay, thank you, Professor Sun. Yeah, so I suppose we start the talk now?
Yeah.
Okay, the first speaker of the conference is Professor Khamsi, and he is a professor at the University of Texas at Paso, Texas, USA. And he did his PhD from the University of Paris 6 in 1986. His present research interests include fixed point theory, geometry of Banach spaces, and operator theory, and also discrete dynamical system, discrete mathematics, order sets, and trusses. He is also author and co-author of six published books, and he also published many research papers in the Decent Journal. He is also editor in the editorial box of 5 international journals, including Fixed Point Theory and the Journal of Mathematical Analysis. He has done a lot in education. He has guided more than 8 PhD students and postdoc fellows. So let's welcome Professor Khamsi for his first talk. Yeah, Professor Khamsi, can you show your talk files?
Say it again, Wong. I'm sorry.
Yeah. So can you share your screen so that we can look at your presentation? So you have prepared a PPT, right? So I hope every other guest mouse your mic for this talk. Okay.
So can you see?
Yeah. Yes. Good. So let me read the title for you. So today the first talk will be on recent geometrical properties of variable exponent spaces by Professor Khamsi. Okay, please, your time, you have 1 hour. Yeah, thank you.
Okay, I'm not able to see you guys, but that's fine. I mean, as long as you can see the screen and you can hear me as well. First, I want to apologize to some people, since this is the first time I'm giving a talk in India, and I'm glad that one of my favorite mathematicians of all time, we are celebrating his birthday in 2 days, or in 1 day, in fact. Again, as I said, I want to apologize to Qamar Ansari, as well as some people like Gopal and Adrian. Some of the ideas I'm sharing with you here, they already heard them. Because since this is the first time, I wanted to share some of the ideas that I'm working on. I'm really right now interested into this and try to understand what's going on. So the talk, the title is a little bit, though the title is about variable exponent spaces, but it's a reflection. It's more than just variable exponent spaces. I will be saying something. And again, many of the ideas are still at the embryonic level. In other words, we did not go deeper yet and understand what's going on, okay? So it has a historical flavor as well as a modern flavor, okay? So you will see. So first, I wanted to, because of for the sake of time, Gopal knows, Dharanjit Gopal knows very well what I'm talking about. If I get into this subject, the one I'm talking about right now, this may need about 3 hours, and I have done that before in King Mongkut University in Bangkok, in Thailand. And so I always get scared when you have 15 minutes or something similar, where you don't give a result to the people, what's going on. In other words, you stay only in the introduction and you don't touch on what's the latest. So let me just start first of all to tell you that what got me motivated, me personally, what got me motivated. I had a student, a PhD student from Turkey, who came to spend a year with me in Texas. And by the way, for the sake of, as you have seen, I'm retiring from Texas and I'm moving to Khalifa University in Abu Dhabi. So that's why. So we are only about an hour and a half. I know that Castillo, El Paso is close to Juarez, and we have almost the same time, 1 hour difference compared to Tijuana. But where I am right now is only 1 hour and a half difference with India. So anyway, so this started when this student came to see me, and I was looking at a problem to give her, and they came by accident to meet this example. So here, the original example published in 1931 by Orlich did not have n+1. It had n. Okay, well, I mean, it's no big deal anyway. It's just re-indexing and you are done. So this example really got my attention. Okay, so the article was written in German, and I don't read German, or at least I'm not good understanding the finalities of the German language. So though it's very close to English, but still. So I looked at it, and I asked a friend of mine, Osvaldo Mendez, to help me out with this. And really, it got my attention. This example got my attention, okay? And what's amazing is that the original article by Orlich in 1931, did not dwell too much on this example, okay? I will say more about it in my talk, okay? So it's just an example, and he moved on, that's what you can see there. What was Orlich thinking when he gave this example? I have no idea. I cannot tell you, okay? Because he didn't say it. Why? But what's interesting is that we're talking about 1931, a period where we wanted to come up with different vector spaces and Banach spaces, okay? So remember, Banach spaces were born in 1922, around that period of time, okay? So what is special about this example, okay? It was Nakano, okay, who took this example to a higher level. The same example, but he took it to a higher level. And he came up with this now vector spaces. So as you can see here, he replaced n plus 1 by pn, or in the original article, n by p of n. So now you have this p of n, and p of n, you can assume that they are bigger or equal than 1, okay? And because you want to have a vector space, etc., etc. In the sense of topological structure, you don't want to have p less than 1, okay? So I don't want to talk about that right now. Let's just stick to what Nakano was doing. And to these vector spaces, to this function p, and again, look now, because I looked to the original article by our friend Orlich, and he doesn't mention variable exponent spaces. It was mentioned later on, but what you can see there is that the exponent is no longer a number in the classical little LP and capital LP. So now you have the exponent that is a variable, and that's why the name came in, variable exponent spaces. In any case, let's continue now. So it was known to Nakano and others, by the way, that as long as Pn is away from 1 and infinity, you inherit the same properties as the little LPs. Okay, so what you want, these two numbers, p minus, which is the infimum, or p plus, which is the supremum, you want them to be away from 1 and infinity. And of course, depending on what you are looking for, okay, what you are looking for, then instead of considering the infimum, you can consider the lim inf and lim sup, okay? But in general, we're looking at the infimum and the supremum, okay? So what happened when p minus is equal to 1 and p plus is equal to infinity? Then the space or the fundamental properties used to establish some of the similar behavior between the classical LP spaces and these variable exponent spaces, they collapse, okay? So people do not touch them, okay? Great. Look at this example, and some in a very simple way will see that, in fact, according to what I was just telling you, that is a simple generalization of the classical LP spaces, okay? LP spaces. So the question becomes, which is really a big dilemma, do we really focus and give it some deep investigation, because it's just a simple generalization, okay? So the question becomes when, oh, I'm sorry, I will come back to that. So here we are. This is the most recent that got me when I started looking into this, that specific example. And I looked at the case when p plus equal infinity, which I told you before that people were not, they were scared to touch the case p minus equal 1 and p plus equal infinity. So we discovered a lot of things, but still we are, as you will see, I'm concluding with this at the end, that we are still just, you know, at the top of the iceberg, or the forest that hides the, I'm sorry, the tree that hides the forest. So you will see it. You will see it in a second that we are touching. We discovered some stuff, some behavior, some nice stuff, and the people are very excited. The people I'm talking about, the Scandinavian and European schools working on these variable exponent spaces, because they did not know what was going on when p minus equal to 1 or p plus equal plus infinity. So we discovered some stuff that I will, I hope I have time to mention it, okay? In any case. So here is the interesting dilemma. So that's what I did. That was the first one, first result. We still, we have few interesting papers on this, and we're still working on this, okay? So here, let me take you back to the interesting dilemma. What is the interesting dilemma? As I said before, LP dot, which is the variable exponent space, is just a simple generalization of what? Of little LP. And therefore, the question is it worthy of our energy and our hard work? So is this generalization worth it? And the answer is, it depends. So sometimes some of the generalizations are worth it and some are not. So the beauty of it is, what is it exactly that you are trying to do? What is the goal? So for example, here, if you look at something that caught my attention a few years back, when somebody, his name is Nawab Hussain, sent me a paper about what's known as cone matrix spaces. So what is a cone matrix space? It's just when you take a distance and you look at the distance, the value of the distance as a vector. So of course, since you want to have the triangle inequality, so you want to have an order between these values of D, then you have to take an ordered vector space. Once you start working with an ordered vector space, so you are looking at a cone, or the positive cone, okay? And that's why we call them, they call them cone matrix spaces. I call them vector valued distances. So the work that was sent to me, and I will give you a reference for it, it was the vector valued distance formulation of the Banach contraction principle, okay? And it was published in a the Journal of Mathematical Analysis and Application, which is one of the wonderful journals in nonlinear analysis. And I wrote to the editor-in-chief about this. How did you allow to publish this paper? And he said that was a mistake in his entire career, that he allowed this paper to be published. I mean, it went through and it was published. And that paper, right after its publication, was it triggered something like 300 papers per year in the following subsequent years. I mean, it took, like, for example, 3 or 4 years where people just went nuts on these cone matrix spaces. And then I published 2 papers to show to the people that, in fact, what they are doing is not a good mathematical work. So in the sense that, as I said here, the answer, it depends. So sometimes it's worth it, sometimes it's not worth it. So let me give you an example on the same vector value distance where it's worth it to do it, okay? So this example is a work done by Agarwal, who in fact was just answering a question by Lakshmikantan. So Lak was asking, I mean, he had the feeling that that's the case, which is that you get a better behavior for some differential equations by looking at a vector value distance instead of the traditional Euclidean distance. So here is the example. So it's a second order differential equation with boundary conditions, and change it to a first order differential system, and you have this approximate solution. It's not an exact solution, but it's an approximate solution, okay? And the issue is, near this approximate solution, you have an exact solution, okay? Okay, you have an exact solution. And what's interesting is that that exact solution has an attractor around it, okay? And what's amazing is that if you take the traditional Euclidean distance, what you see there is a disk around the approximated solution that you see right here, okay, with the delta, okay? But when you use the vector value distance, you find, in fact, that you have an attractor which is, in fact, unbounded, okay? So it's a strip that is unbounded. It's really amazing, okay? So what was the distance used by our friend Agarwal, Ravi, using, as I said, in this example, it was Lak that had the idea that this may happen, okay? And it was, of course, Ravi who carried on this calculation. And so the distance is this one. In our example, in fact, is R2 here, okay, in the previous example. And what you do, the distance now becomes a vector in Rn. And here is the formal definition of what is a vector value distance. I told you it has to be an ordered vector space. The V plus is the cone, and you have the traditional definition, okay, of the distance, and you generate what's known as a vector valued metric space, okay? And from there, you define the entire topology associated with it, including the sequential topology about completeness, quotient, and so on and so forth. And then you have this beautiful theorem that was published a long time ago, okay? And this is the theorem that was proved by Ravi, which can be seen as the analog to Banach contraction principle. Here, the A is an operator, and a positive operator, meaning that the cone, you send the cone, positive cone into the positive cone, you assume that the spectral radius is less than 1 because you want the iterations to go to 0, and you have what you know of Banach contraction principle, but given in this formulation, okay, in this formulation. And again, the motivation, as I told you, is the idea of that attractor that was bounded if you're looking at the Euclidean distance. But if you look at it from the Euclidean distance to the looking into it using the vector valued distance, then you end up having a bigger domain, okay, a bigger attractor, sorry, not domain. Okay, so the paper I was telling you about that was noteworthy is the one that was published in 2007. By the way, the original paper by Ravi was published in the 80s. So the one that was published, which uses the same formulation of that vector valued distance, the one I gave you, the general formulation, okay, with the ordered vector space, etc., etc. So they gave exactly the same theorem of Banach. But again, if you go back here, what they did, they put k. So d is a vector, but they multiplied by a constant k less than 1. In other words, the same idea as what? As the original Banach contraction principle, okay? The original contractive map. So that's what you have. So in fact, if you think about it, the work by Long Quang and Xian, in fact, in 2007, is just a simple corollary of the original result by Ravi that was done in the 80s, 20 years prior, okay, 20 years prior. And what's the constant, in fact, even the proof assumes some crazy assumptions like that the cone has to be normal, etc., because some people, when I attacked this case, and they published 2 papers against this, some people in Eastern Europe wrote articles where they put my name in the abstract, saying that I missed the assumption that the cone should be normal and this and that and can't be done, blah 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 blah. But in fact, we know now. I mean, it's nobody is publishing now in cone metric spaces. So if this really was worth it, it would have survived, but it didn't survive. So first attack, we went from 400 papers, 300 papers per year to almost none. I understand that, as I always say, that some people are tempted because of the pressure that we have right now to multiply publications, but one has to be extremely careful. Yeah, okay, fine. I mean, because of promotions, jobs, etc., but we don't want to just start publishing for the sake of publishing. I'm not going to tell you what Bozami in France once said about people publishing. He never understood why people are publishing, because history will always judge the quality of what you are writing in any case. So in this case, here is an example where to take the vector valued distance, the work done by Ravi and Lakshmikantan, because he's the one who had this initial idea, and look at the work done since 2007 on these cone metric spaces. So sometimes there is a value in looking at certain generalizations, and sometimes there is not. Okay, it's like these abstract formulations. If you think about Banach contraction principle, it's just the theorem by itself was known to Poincaré and to Penaud. I'm sorry, to I always have a problem with this guy. In any case, so it was known. It was known for many years prior to Banach. So what was special about Banach's work in 1922 in his PhD? The idea was to give this abstract formulation using a metric space. Before, it was known in specific cases, mostly in function spaces. So the vectors were functions before. Right? Same formulation, same conclusion, but it was done in function spaces. The case of Banach, he looked at it into the abstract space, which is a metric space, okay? And he gave that beautiful formulation. And again, nobody would have thought that one day fitting I'm talking about fitting, throwing at you. If somebody needs this paper, I have it, by the way, or a reference, who looked at a logic program in artificial intelligence, stratified program, and explained it. Why do we have one stable model by looking at a unique stable model that we get after omega iteration is because of the Banach contraction principle. So he defined the distance, and he explained that the operator involved is a contraction, and that's how we get only one model, stable model, that and we get it into omega iteration. Okay. So this is really something I'm passionate about. So what is exactly in this generalization that I wanted to show you here is the concept of a distance. Okay, distance. What is a distance? So this concept, I started working on it around 1986. So we're talking about almost 35 years ago, okay? And it's really puzzling to me, okay? And if you think that why are we doing this? Why do we want to know this? So let me take you back. I want to take you back. Okay, so focus on what you see in the definition. Ignore the fact that D is a vector value. Just focus on the definition 1, 2, and 3. I, double I, triple I. So this is what we teach our students in intro analysis course, whether it's senior undergraduates or first course graduates. And how did we get to this definition? Okay. So if you look and you do a little historical search, you will find out that the people are saying that this definition is due to Fréchet. The way you see it was published by Hausdorff in 1914 in his famous book. It's in German, by the way. That was translated. The third version was translated in 1954, but to English. But the original book, which the title is Basic Set Theory. Basic Set Theory. The second version, I believe, or the third one, he removed basic, and now it's called set theory. Okay, set theory. And it's really amazing how what you see there has to do with set theory. Okay, and you will see the topology, the metric topology coming from there. That's the beginning, by the way, of what's known as topology today. So I have said what I just told you right now. I have said it in many places worldwide. In fact, last week, while I'm preparing my talk for both the conference in Saudi Arabia and here, I decided, you know what? Let me read Fréchet's thesis, okay, in 1906. So I downloaded the thesis. I found it, and I downloaded the thesis. It's written in French, and I read the thesis. And in fact, there is more to the story. I read the whole thesis in one shot. Okay, I started, I finished it, and now I know what's written in that thesis, and I know what Fréchet wrote in his thesis. And what's interesting is that he has two categories. Okay, what he calls class E and class V. Okay. V for voisinage and E for écart. And what we inherited from him as the distance is the class E. Except what? That in the class E, he has condition 1 and condition 3. But he doesn't have condition 2. Now, if you look at all the examples, you will find out that his examples, the condition 2 is satisfied. Okay, but as I told the people before, the condition 2 is not natural. It is natural if you are in Euclidean geometry, the distance between 2 points. But it's not natural if you are, for example, driving. If I tell you what's known as the, for computer scientists, as the flower shop problem, if I tell you I'm driving to get some flowers to my wife, and I'm going to the flower shop, I drive from my home to the flower shop, the distance between my home to the flower shop will not be the same as the distance from the flower shop back to my home. By no means. Okay? And to understand why is that is because what is the fundamental difference between this and the Euclidean geometry, where obviously the distance between A and B is the same as the distance from B to A, is because we are not moving freely. We are moving along a weighted graph, along a network. And once you start moving on the network, so you are no longer free to do whatever you want, okay? Especially when you have an oriented graph, in this case, the roads, basically. Yeah? Some of them are one way and some of them are both ways. So you have this oriented graph and you are moving along this oriented graph, and it's a weighted graph because you are taking what? The distance of the edges, okay? That's because I'm computing the distance between the flower shop to my home. And then you find out in a very natural fashion that 2 fails. Yeah. Which brings me to the issue of what's going on here. In other words, what is the distance? Okay. And how can we come up with a concept of distance that indeed is more abstract than what we have learned so far? In other words, that the classical metric spaces that we are teaching and we are learning and we are working with are just a special category. So what is it? Okay, so this is what for many people working in discrete mathematics and set theory is still a problem that is open. And as you can see, what these people did, whether it's Lack and Ravi Agarwal, as well as Long Wang and Xian and others, is just to touch on that question. But they didn't go deeper. It was motivated by other issues that I don't want to discuss here. Okay? So here, 30 years of work with Maurice Puiset from Lyon. And we finally had a paper that we had major problem publishing, I'll be honest with you, in the sense that it's extremely hard to read. And at the end, when it was accepted, the editor-in-chief asked us to cut the length of that paper. It was really a big paper. And we had to cut the length to a certain number of pages. And did we answer the question? The answer is no. We have now an abstract formulation of what is a distance, okay? But just to give you an idea, for example, you can look at graphs as metric spaces, okay? So, and really it's something like, for example, very interesting, how can you define the distance between 2 texts, 2 poems, for example, okay? Stuff like this, okay? So it's just interesting problem. It's still, as I said, is the grail where we are still working on this problem, and it's still an open problem, okay? So let me go to now variable exponent spaces, okay? So before I go into these variable exponent spaces, let me just give you, let's start from the beginning. In other words, what is the roots? So remember, I gave you the example of 1931 that was published in our friend Orlich's original paper, okay? But let's go prior to 1931, the concept of Banach spaces. So Banach spaces, you have to go to 1922, or at least 1920. They knew about completeness, by the way. They didn't call it the word complete. So it's really interesting. If you read articles of that period of time, you will be amazed how they used to say the stuff, okay? But they knew, for example, that the case of, if you look at the case of Q and R, okay? If you look at Q, the rationals, then you can have a Cauchy sequence that doesn't converge. Of course, it goes back to Weierstrass and Cauchy and others, okay? So we're talking about the real topology or the topology on the real line, okay? There are Cauchy sequences which do not converge, and there are Cauchy sequences which converge all the time, and that's your famous construction of the reals as the completion of the rationals, etc., etc. So here, they didn't call them complete matrix spaces, they called them something else, okay? So this goes around the same period of time. So we're looking at the people with major influence on the development of what's known as function analysis, okay? So you have 1902, Lubeck, with his integration. That was a major revolution of the time. You have the Friedholm and Volterra and so on and so forth for the integral equations. You have Hilbert, of course, who is considered as one who influenced the modern mathematics in a real sense. I ask all the students to check, for example, what are the 10 problems that left by Hilbert, that he said that these are the ones that will affect and will be the major development of mathematics in the next century. And in fact, the field medalists are the ones who are working in the same areas that was defined by Hilbert in his writing at the beginning there. 1906, Fréchet, okay, and it was a question by Adamov. So as you can see there, you are not talking about some simple names. These are the founding fathers of modern mathematics, okay? But as you can see, they are all around the same period of time, all of them, okay? So there is absolutely no concept of a distance yet. So they were working with specific examples, okay? Specific examples. Just to give you an idea, capital LP was not born yet. Yeah, right. What you see there, that period of time, they didn't have the concept of capital LP. They had the concept of continuous functions. Yes, of course, with the supremum norm. And there was no norm, by the way. The norm came later on, okay? So this is exactly what the problem is when you look at an integral equation. I was reading an article, a beautiful article, a historical one, of course, where they take an integral equation and they approximate the integral equation by a linear system. And they had a problem because I'm talking about the mathematics of at the time, okay? So they approximate by a linear system, but the linear system was finite dimensional. The number of unknowns was finite. And the beauty is when you move into an integral equation, then you are approximating by a linear system that's becoming bigger and bigger, in fact, infinite. And they had this problem, really they had this problem to work with, which is infinite matrices, infinite linear systems, infinite dimensional stuff. And they were really lost at the moment. It wasn't like a very well, like for example, eigenvectors, as you can imagine, how do you define? They knew before because of the determinant and so on and so forth. That's all what they used to do before was finite dimensional. But now they are talking about what? They are talking about infinite dimensional object. And look what Birkhoff said. I mean, he said that it is my private opinion that Hilbert never mastered the Lubeck integral. And this is really interesting because to do that approximation, and Hilbert worked with this, to do this approximation, what you can only do is to take a function and approximate the function by its Riemann sums. And that's how you discretize a problem, okay? And that's what they did, by the way, exactly what they did. So now what's amazing to me is that this cannot be done if you're looking at the Lubeck integral. And this Lubeck integral really puts a major dent in the fundamental understanding of what is a function. And that's why Hilbert had problem with this Lubeck integral. Okay, so a function is no longer a function. And this reminds me an article that was published after Einstein's famous article, where it was published by scientists, where the title was "The Second is in Danger." Okay, because when Einstein told them that time is relative, the people they were shocked. And right now, as you can see, to say that Hilbert never mastered the Lubeck integral is something amazing to me. Of course, if I told you this, myself, you would have a little bit been skeptical. But anyway, the point is that, as I tell my students, every time that somebody is telling me capital LP and little LP are similar, I mean, I used to believe that, okay? So the capital LP and little LP, one is a special case of the other one by looking at a purely atomic measure. Any question? I heard some noise. I can't see you guys. Sorry. Huh? I'm almost. You see, I'm.
Well, it should be okay. It should be okay. So we hear you.
No question. I can see you. I can see you. That's why. I'm really sorry. So again, as I said,
I'm here. Yeah, no problem.
Okay. So capital LP was born in 1907. From the work of Fischer and Ritz. And of course, we all know about the work of Ritz in L2. So as you can imagine, of course, here based on the Lubeck integral. Of course, now we're looking at the Lubeck integral. Because before, as I told you, a function, you have to go to the old traditional definition of what is a function, okay? And now Lubeck has changed that. I mean, you have some awful functions, they become extremely nice. Why? Because in the Lubeck mind, f equal g does not mean f of x equal g of x for every x. You understand now? Huh? And many of our students, unfortunately, do not master Lubeck. And we go and we take them to the abstract measures. That is the biggest mistake you can do for somebody like that. Okay? Please understand Lubeck first. Try to understand what's going on with the Lubeck measure, taking you from the Riemann integral to the Lubeck integral. It's a major change, and fundamental change there, right there, okay? So in any case, these spaces, what's known as classical spaces or classical Banach spaces, they were born after the people, 1907, okay? And it's amazing that little LP, and that's why, because at this stage, no measure, no abstract measure. We're just looking at the Lubeck integral. And what's amazing is it took another 6 years before we saw what? Little LP. So when somebody tells me little LP and capital LP are the same, I lose it now. Now, of course, when I was a student, I accepted that. And as you can see, quickly, little LP enjoys properties, especially, the weak topology, the weak topology. Now we're talking about Banach's school in the 30s, where we started to have this fundamental and Banach theorems and all the fundamental theorems of function analysis. Then we have now something called the weak topology, which, by the way, what's his name? Fréchet worked with, but he did not know it in that formal stuff that we teach to our students that was born in the 30s. So the weak topology between capital LP and little LP, I mean, guys, I'm telling you, it's an ocean between the two. When you say capital LP and little LP are the same, you are really hurting whoever is learning these materials, hurting him. They are totally different, okay? When you look at the weak topology in capital LP and the weak topology in little LP, the weak topology in little LP is more connected to the pointwise convergence in capital LP, okay? But has nothing to do. The other one, you have other convergence like the convergence in measure and so on. It's really complicated. It's really complicated. Anyway, so what is exactly I want to talk about? Let's go back to the Hilbert space, and you have the famous paragram identity, okay, that you have in capital L2. It comes from the real line. It comes also from R2 and Rn. And it's very simple to obtain this one, which is not known by the student. And here, this one is interesting. It has a property that, hold on, control, how do I exit? Okay, so this one here, okay, this one, it's interesting because what it tells us is if you take the unit disk, okay, and you take, I'm talking about vectors, okay, and you want these vectors to be far from each other, okay, not too close. Then if you look at the middle point or the middle vector, it's inside. But it's not just inside, it's really inside. So you have a control here. You are far from, see, the control is right here. You are far from the surface. I'm sorry, the sphere. And this control, the calculation here, this control here, is given with how far the two vectors are. Okay, the two vectors are. If they get closer, the middle one will get closer to the sphere. But the uniform control, is what the one who did it is Clarkson, and this is. You see it right here. Huh? So if you have the norm less than 1, norm of y less than 1, and they are far from each other, okay, there is a control, then you have the vector, the middle one is inside, but far from 1, which is the sphere, okay? And that was done by Clarkson in 1936. He's the one who noticed this. Okay, now, if you want to do it for LP, okay, so you need an inequality that is satisfied that he's going to use, and that's the one you see right here now, okay? And what I want you to understand is the control is coming from here. See, this term here is what will give you the control, okay? And this is just a property on the real line, huh? So here you get this, and then you get this. So that will give you similar control, and that was the paper published by Clarkson where he proved this in capital LP and little p, and he called it uniform convexity. Huh? That's what he called it, uniform convexity. Okay? So what happened when P is less than 2? By the way, if you go back here, what happened to LP when P is less than 2? They got it by duality, because the dual of LP is LQ, and if P is bigger than 2, Q is less than 2. So I'm not gonna talk about the geometry of Banach spaces where it shows that uniformly convex, the dual is uniformly smooth, and if you are uniformly smooth, the dual is uniformly convex. So what you want to show is that capital LP is in fact, for P bigger than 2, is in fact both uniformly smooth and uniformly convex, and that's how you get that LQ for Q less than 2 is also uniformly convex and uniformly smooth. But if you want to do it by hand for other reasons, including the issue of variable exponent spaces that Sandera-san worked on, okay, then you need another inequality. Complicated. I mean, this inequality is not simple. I'll be honest with you. It's a challenge. And again, look at the middle. The middle is right here. And this one is what's going to give us, again, that control to be inside. You see, this part here. Okay? But what happened here is this part, though it has a minus b over 2 here, the same as the other one before, but now you have this p times p minus 1. This is terrible. Why? Because when p is close to 1, this control dies. So when p gets closer to 1, this control dies. As long as p is not close to 1, you are okay. Do you see it now? Do you understand now why we got that idea that p minus bigger than 1? That's coming from this here that you see here. Okay. Okay, so Orlich, what did he do? Orlich, I'm going to go a little bit faster because I want to touch on something else that's also interesting for the younger mathematicians. Orlich, in his paper, he gave that famous example I showed you, that amazing example. But quickly, he moved away from it, and he came up with another example. That example took off, and that example became extremely popular, okay? Where you have a school in Poland around that, and of course, even a school in China, and I'm referring here to Chutao Chen, which, by the way, I published a paper with him, and we wrote in the paper Chen Chutao, but it should be Chutao Chen. He did work on this because of his advisor who got jailed during the anyway. Well, I'm not going to tell you the history of the Orlich group in China. That's for another day. In any case, so what is the example? What Orlich did, he said, okay, let's take the LP spaces. And what defines the LP spaces is the function t to the power p. Okay? So he replaced t to the power p by a function phi. And he assumed that similar to t to the power p. Let's not open the subject. It's an ocean there. Let's not even open it, okay? Let's just stick to simple to understand, and then we can talk about complicated. So look at a function, a graph function, that is as simple as t to the power p. Same behavior, same properties, okay? And now consider this. That was in his paper, by the way. The integral from 0 to 1, you can put it in any integral between any sets you want, that's fine. But look at now this. Okay. Of course, if you take t to the power p and you go back to capital LP, there is no lambda. Why? Because lambda will come out as 1 over lambda to the power p, and then you are okay. Then you don't need lambda. But in fact, it was done by him. I'm talking about by Orlich. Okay. So this is the LP spaces or Orlich spaces. Okay. So he went away from the amazing example I told you about. Okay. Now. What is the norm? So the norm, we call it the Luxembourg norm because of his work with Zenin on the function spaces. He has a fundamental work done with Zenin on functional analysis or functional spaces. But in any case, this is just a Minkowski functional. Okay, the norm that you see there is just a Minkowski functional of a balanced convex set, and you have it. But what I want you to understand, this is the classical Orlich norm. So you have Orlich space and the classical Orlich norm. What's the difference now? Right there, 1930s, we have a major problem. What's the problem? The problem is that the norm and the integrals are defined in a complicated, indirect way. And that's why when the people, they wanted to study properties for Orlich spaces, all the properties that we know in the classical case, they are really, it's extremely complicated. You have no idea. okay? Including, like, for example, the work by Clarkson, which is the uniform convexity, okay? It's complicated, extremely complicated. We are going into a different dimension, going from the classical LP spaces to the case of Orlish spaces. Okay, so what's amazing is that Orlish did not see something. He did this, yeah, and also the Orlish school, including Mushilak, because they developed the whole school in Poznań, in Poland, but they did not see something. It was Nakano saw something in this work, okay? So the idea is that that integral that before gave us the norm, and that's it. Now, it was Nakano 1950 who saw this tool that he called the modular. He called it the modular. Don't ask me why, guys, okay? And that's why you see that famous book, Modularity Semi-Ordered Linear Spaces, okay? So he saw the concept of a module, which is that integral that you see there. You see what you see here, right here, okay? So the norm is coming from this object, yeah? And he said, okay, so now he came up with the concept known as the module or the modular defined on a vector space. So again, what do we have? We have vector spaces that was known before. We have the distance, 1920s, the norm formal by, and he called them spaces class B. I'm talking about Banach and his friends, and that's the norm, okay? And now we have this concept of what? The modular. And that was done by Nakano, which, by the way, is more general than what? Than the norm. The norms are a special case of regulars. So what is the fundamental problem is number two. This is terrible. Number two tells me what? That I don't have homogeneity of the norm. Yeah. Homogeneity of the norm plays a major role. We don't. Because if you go back here, you don't have it. Because phi can be any functional, yeah. And any function, sorry, any function. And here, you don't have the triangle inequality. You don't. Yeah, you don't have the triangle inequality. Neither 3 nor 3 prime. It doesn't matter whether it's convex or not, but you don't have the triangle inequality. You don't have the triangle inequality, you are in trouble. Why? Because what is rho of 2x? The rho of 2x is going to be rho of x plus x. And if you were having the triangle inequality, it will be less than rho of x plus rho of x, and that will be 2 rho of x. But since you don't have it, then you may have a problem with rho of 2x. So in other words, rho of x may be finite, and the rho of 2x may be infinite. And by the way, it's an extended function. Huh? So rho can take the value infinity. All this was known to, by the way, Nakano, okay? Okay, so to a modular, we have a vector space, and we have a norm that we also call the Luxembourg norm, but in fact is not. It's the Minkowski functional, and you have this norm. So you have a normed vector space, okay, from the modular sense. And the example, of course, was the Orlish spaces or modular function spaces. In 1988, when I met this object, I worked with Kozlowski, I worked on modular function spaces, okay? So remember I just said rho of 2x and rho of x, and the people quickly, they saw that, including Nakano, by the way, that central concept for the study of modular vector spaces is what's known as the delta 2 condition, okay? And that's, you have different types. They are all falling under the same type and the same idea, which is that rho of 2x is controlled by rho of x in some ways or some other stuff. So, okay, here, and if you go back here to our example now, okay, and I'm going to stop right here, is the fact that this example, amazing example by by our friend Orlich, if you take the vector space x equal r to the power n, and you look at sequences, and you define this object, you generate a modular. And what's interesting about this modular now, this one here, is it doesn't satisfy the delta 2 condition. Why? Because if you put a 2, you are going to have 2 to the power n plus 1 out, and it may become infinite. Yeah. Do I have more time, or shall I continue, or shall I stop here?
I think your time is up. So
okay.
Can you make a conclusion?
By the way, Professor Sam, I have the entire paper, which, by the way, I am just at 52 slides. I still have about another 57 slides left, but I can send it to you, and you can share it with the people, okay?
Yes, please. You can certainly send it.
I talk about, this new modular uniform convexity that we discovered with Chen Shutao, and the usefulness, and how some cases where p plus equal infinity is okay, where we fail the delta 2 condition, but we still have some amazing behavior. Yeah, some amazing behavior. So I will stop here. There is more to it. There is more to the story. Okay.
Yeah, thank you. Yeah, it's a very interesting and very informative talk. I think every one of us learned a lot from the speaker. So is there any question or comments from the audience?
It is, in fact, a very thought-provoking talk, and really very interesting, and giving a very, very deep understanding of the distance concept in different spaces. Really, I am sure that all the participants are benefited largely. And I hope that Professor Khamsi will give some other time to finish his another 50 slides. In some other session, we will have him over
why
here.
Not?
And I am certainly thankful to Dr. Gopal, who has given me this opportunity to invite you. And I'm really, but I know you from a long back, but I have never met you, or whatever it is. So really, really wonderful talk.
Oh, yeah, please, Professor Sai, do you have a question or comment?
Good morning, sir. Myself, Hardeep Singh from Aligarh Muslim University, India. Sir, I have a question.
Yeah, go ahead.
Sir, you have given the definition of the uniform convexity. How the convexity is linked to the uniform convexity? That is there any relation between the definition of the convexity and uniform convexity?
You mean convexity and uniform convexity, right?
Yes, sir. Yes, sir. Actually, in uniform convexity, term of convexity is used.
Yeah, the terminology is coming from, as I told you before, from the convexity of the unit sphere. Okay, but the problem is, if you just stick to the the convexity of the unit sphere, you end up into what's known as the strict convexity. You need that uniform control, and that's why you have what's known as uniform convexity. And in the original, some of the original work, it wasn't called uniform convexity; it was known as uniform smoothness of the sphere. Yeah. But there is more to it. There is more to all this. At the end of my talk, I talk about what's known as uniform convexity in every direction. That was Karkavi's work, and strict convexity and the connection between the two, and so on and so forth. There is more to the story. There is more. I wanted just to go to the beginning, where things were simple. It got complicated, but if you understand first the beginning, and you have solid understanding of the beginning, then you can do complicated stuff. That's what I try to do.
Okay, sir. Thank you.
Okay.
Yeah, please.
Yeah, please.
I know you're gonna say something. I would have been surprised.
Professor Khamsi, it's our pleasure to, by any means, to listen you. We understand it, especially the people who really have been I mean, heard or witnessed your lectures and the stuff. Only thing by interest myself, I just wanted to little bit know if it. What about the best one, the ordering? If we can do something there, please, if anything in your mind, please, for us.
Again, then she say it again.
My point is some kind of the order structure or some graph theoretical aspect in modular sense.
Oh, yeah.
Is there any possibility for us?
Yeah, we did. In fact, again, I'm so sorry to take time from you guys, but keep in mind, okay? What I wanted to say is that if we don't have a better understanding of the original part of what you learned today, all the modern mathematics, all of it, from computer science, I'm talking about mathematics, working with computer science here, or physics, mathematics, etc. If you don't understand the foundation, okay, or you have a confusion about the foundation, you will keep carrying this confusion all through. So my point is, what do we do now? Yeah, we do some amazing stuff. Like, for example, the idea of what I called order uniform convexity. So I only assume that the middle point is inside the ball for comparable elements. Okay? So why? Because all the natural classical Banach spaces are ordered. Okay? There is a natural order there. Okay? I'm talking about function spaces, etc. You have a natural order. And therefore, we have this concept known as order uniform convexity. And what can we do with it? Okay? So, yes, we do have that. And we published a paper on this. But to the best of my knowledge, it's fairly recent. So, the best of my knowledge, it still did not pick up a little bit more attention. Yeah. But I can send you the link, Dharanjay, okay? I will send you the link or the paper itself, okay?
Yeah, thanks a lot. Thank you.
Kamar! Oh, Kamar, I see Kamar. I'm sorry, guys.
I have a question.
I'm really sorry.
I have a question.
Sure, go ahead.
Both of you and Professor Wong.
Okay. Oh, yeah, sorry, please.
So when you both will be coming to India?
I swear, Kamar, I knew you were going to do it to me. I knew that.
When can I see both of you in India?
Okay.
Yeah. Before. Yeah. Soon.
We should get them, certainly. We should get them sometime next year.
Thank you, Kamar. Thank you.
Okay. I think maybe we should end this section and you leave the private communication to you later. Okay, so we thank the speaker again. Let's just say thank you. Yeah, thank you very much, Professor.
Thank you very much, guys. Thank you.
Yeah,
thank you.
Okay, so Professor Shum, I return it to you.
Yes. The first talk is now.